Right, so today we'll talk about KV caching. What is KV caching? We'll go in details and why is it needed. Before that, I recommend you watch some basics about LLM text generation and how about transformers in general. Basic how text is generated. Maybe refer or skim through the paper of attention is all you need, and you'll get to know about these matrices which you had WQ, WK, and WV. Right, a good bit of introduction should be good enough for you to understand KV caching. Right, so let's start. We know that LLM text generation in general is nothing but a bunch of matrix multiplication happening in parallel on the GPUs. So let's first talk about basics of matrix multiplication, basic things. Right, so this is nothing but a bunch of numbers. This is a 3x3 matrix and it's 3x1 matrix. So if you have a cross B matrix, in order to multiply it with another matrix, you need to have a B cross C matrix. So the number of columns in the first matrix should be equal to the number of rows in the second matrix, and you get the resulting matrix size as A cross C. Right, it's the matrix basics things. Right, now for the transformers, when you train a particular LLM model, you get three different matrices called WQ, WK, and WV. These are made after lots of training data. These are parameters tuned and tweaked, and these matrices help us to generate the next set of tokens. How? Let's see that. For that, to generate the next set of tokens, we need three new matrices called K, V, and Q. If you refer to the original tensions, all you need paper, you will see the mention of these three matrices, and the actual formula for computing attention uses all three of these. Right, how do we compute these? We use the original matrix matrices which we've developed from the data, and we multiply those with the embeddings. Right, the embeddings, what is an embedding? Right, so an embedding is nothing but a vector, you can say a bunch of numbers which we've generated for a particular token. So say you have a prompt here, right? What is the capital of India? You break this prompt down into different set of tokens, a list of tokens. Now each token here is generated from a vocabulary that you have. So we have a vocabulary, and this vocabulary contains different tokens. It could contain DIA, it could contain ITAL, and different. So based on this vocabulary and a particular tokenization strategy or algorithm, you break this whole prompt down into set of tokens. Now this is just a sample tokenization. This is not a real tokenization. This is just for an example, right? So each tokenization is, after tokenization, each token is broken down into its embedding. You can just pass it to an embedding model and get some embeddings. These are nothing but base embeddings are nothing, just a particular token has this representation in a vector form. Right, this after this representation is made, we have the dimension of this particular vector, the number of rows here, as dm. Okay, we'll call it as dm. So here we'll need some matrix multiplication and the usage of this A cross B and B cross C. Right, so we'll just call it dm with the embeddings. This is one row. Right, now when we're saying embedding E, we're actually trying to say not just single row, not just a single row, but the whole thing, and the shape of this whole thing is going to be T cross dm. So this is actually going to be rotated by 90 degrees. Right, so this is rotated by 90 degrees. So it would actually look something like this, and this is the way its embedding is going to look. Right, each embedding, so the number of rows it has is T, and the number of columns it has is dm, right, which we talked about here, that each row of this embedding vector has number of rows as dm, right? So they have dm different numbers here, right? So this is the shape d cross dm, right? Now another thing is, say you're taking wq, so wq will have a shape of dm cross dk. Dk is, we're just calling it as an arbitrary number dk, right? This is dimension. So as you can notice that the dm here in embedding and the dm here in wq, they are matching, so they can be simply multiplied easily, right? Based on that, we can compute the E cross W, which gives us the Q matrix, and so similarly we can compute the key and the K and the V matrix. So the resulting shape would come out to be T cross DK, right? Again, the DM is the embedding dimension that we call it. Now let's come to K and actually go through the computation walkthrough for K, right? So you have this K matrix, right, and you have this E matrix, and you have the WK matrix, and number of tokens is represented by T, right? So the resulting would be again the T cross DK. Now when we have the first set of token, I just I enter the prompt of what, right, and it just takes this one thing as token, right? Just send it one token, this one single token, and say the dimension of the embedding vector, that the embedding vector, the embedding you get after converting that token into actual numbers is just 2 rows, and dk, the arbitrary number of k, is 3, right? So we multiply this T cross dm, which is 1 cross 2, this matrix, this is the embedding matrix, and we multiply that with the WK, which is made from data, right? This is 2 cross 3 matrix, and we multiply that to get a 1 cross 3 matrix, which is the K matrix, right? K1, right? So this is for token 1, just a single token, right? So from this single token, the LLM is going to generate a new token. Say I don't know, say if you have a prompt of what, maybe the next set of token can be what is, right? Or it could be, the next set of token could be what can, like say what can you do, or what is this, right? A different set of tokens that can be generated by an LLM, right? So the LLM generates the token, right? So we get now 2 tokens. So it could be just is or can. Let's just choose can for now. So now we have two tokens, right? Once we have 2 tokens, we need to pass these whole new set of tokens, this new set of tokens, the what and can, into the LLM again to generate the new third token, right? So we already have the embeddings for this. We need embeddings. We will compute the embeddings for this as well and push it back to the LLM, right? Now this whole thing is called auto-regressive generation. So once we have this next token, we have the number of tokens to be t is equals to 2, right? So the new k would be computed as this. So this is the new embedding, right? So notice how the old part of the matrix is the same as here. We only have attached a new row, which is the new embedding of can, right? We had what, and now we have can, right? So this is the token 1, this is token 2, this is the embedding of token 2, 2 and 3, and the wk remains the same. Okay, this is 6, there should be 6 as well, right? So now the computation happens again, and if you notice that this particular row from 5 11 17 and 5 11 17 remains the same, the only catch here is we get a new row attached in the k, right? So if you are noticing the extra computation, that we already had 5 11 17, but we had to compute it again because we did not save it. So that is what KV caching is all about. You cache this particular row, right? So you can cache this particular row into memory, and you just generate this new row for the LLM text generation. As simple as that, right? But then comes a question that why the hell is it called KV caching if we have K, V, K, V and Q matrices? What about Q? You would say, what about Q? Well, we'll come back to it in a bit, just in a bit. But before that, I just want to be very clear that I want you to be, clear that we are only trying to save memory, save computation cost, so that we can reduce time and just, actually give the answers to the users faster by actually caching these tokens and just only generating the next set of tokens that are needed. This K and V, these are needed to generate the next set of attention tokens, right? Now let's come to what about Q and why only KV caching. Well, the question here comes, do you really need to cache Q? Well, you would say yes. I saw the formula for just say KV, let's say attention formula, and if you go, then this is the formula, right? Attention for attention, like QKV for the attention is computed as softmax QK transpose divided by square root of DK multiplied by V, right? So we do need Q and we can cache Q, right? Can we not? And this DK is the same as, we were talking about here, this DK here, right? But then I ask you, I ask you, why do we need to cache Q if we are doing an auto-regressive decoding, right? What does an auto-regressive decoding mean? It means we are generating tokens in sequence one by one, right? So we generate the next set of tokens. We have a set of tokens 1, 2, 3, 4, and in order to generate the next token, we push this whole thing into the LLM to generate the next token, right? Once we generate this token, we again push the whole thing including the new token to generate the next token, and so on, right? So we're only actually using this to generate the token one by one and then pushing the whole thing again, right? So the actual use of Q query is not actually needed, because we're not using the whole queue but only the particular QI. It would be more clear with this particular formula. So this is from the VLLM research paper. What is a VLLM? You can just look it about it on the internet. They introduced overall this whole caching thing and the computation optimizations. So the whole research paper actually tells you that to compute the attention head of AIJ, to compute this particular attention head AIJ, you take the exponential and just say, this is you just like saying a softmax of QI transpose KJ. So notice the actual formula here written is different. Well, that is not actually related to that. This is different for computation and understandings. You can read more about it, why it's actually written this way, but not focusing on that. We need to focus on the actual indexes here, right? So it's not actually using the whole Q vector. If you look at it clearly, it uses for computing attention head of AIJ. We are trying to compute the AIJ, and we take QI here and KJ here, and OI is sigma AIJ VJ, right? The output OI the output OI is this whole summation, right? And you compute the attention score for IJ as this value, right? So if you write it down, you're just simply writing this summation as exponential of Qi transport Kj divided by square root of t divided by summation of t equal to 1 to I exponential of Qi transpose Kg divided by square root of t, and this goes from j equals 1 to I, and you actually compute the output OI. So here notice that I is fixed, right? So for a particular sequence output, say you want to compute O2, the output 2, you would be taking only the query Q2, not the entire, the Q, small q represents to, the particular index here. So you're actually not using the entire Q, just that particular portion, and you're iterating over J. So for J, you're iterating from 1 to I, you're iterating over the all values of K, right? From K1 to Ki, you're iterating over all values of K, and again this whole thing is multiplied with Vj. So again you're iterating over all the values of V. That is why we are trying to cache K and V, because we need these values from the starting till the current index, but in case of Q, we only need this particular of that particular index, not the previous values, right? We don't need Q1, Q2 to compute some Qi, right? But in case of K and V, we do need those values. That is why we're trying to save this into our cache memory, these previous values. That is why we are doing the whole KV caching thing. I hope this is all clear, and makes sense. And thank you for watching. I'll see you in the next video.